Hello. In this video, I'm going to give an introduction to what's called entropy. And entropy is an important quantity when we talk about energy. You may recall from the previous course in general chemistry that we had this idea of enthalpy, which is a form of energy transfer in chemical and physical processes. So today what we're going to do is we're going to look at another quantity which is used in thermodynamics, which is called entropy. Once we've done that, we'll connect it into something called free energy and then to equilibrium. So the title of the chapter is Entropy, Free Energy, and Equilibrium. So we're going to start with entropy here today. Okay. So entropy can be thought of as a distribution of energy states. Okay, so we have this idea of energy, right? Energy is the capacity to do work. So for example, it takes energy to move a block up a hill, for example, or it takes energy to move an electron from a proton to another atom. That requires energy or work, right? But what we're concerned here is with what we call the distribution of energy. Okay, so energy can be useful or it can be not so useful. So for example, if we have energy in a battery, that might be pretty useful. But if we have used that energy in the battery, that energy has now been converted into sound waves, perhaps if there's a speaker, or into light, if there's some sort of display, right? And so that energy becomes less useful. And so what we're interested in really, in a sense, is the usefulness of energy, and that's how entropy is connected to it. The lower the energy, we would say the tighter, the closer the distribution of energy. So imagine I say, hey, I have a lot of energy and it has this value. We would say there's a very low entropy for that. So this is energy, right? So see how narrow that distribution of energy is? That's what we would call low energy, or sometimes people will just say low disorder. But now imagine we use that energy to do something and it gets distributed throughout space in maybe even in different forms, and it looks something like this. Now we have a nice broad distribution of energy, right? So we would say that this is high energy or high entropy and large disorder. Okay, so we're going to use the symbol for entropy. We're going to use the symbol a capital S and uppercase S. So that's our symbol for entropy. And often it's the case that the entropy, which is quantifiable, we can come up with a number for it. The amount of entropy that a set of energies has, a quantity of energy has, is proportional to the spatial distribution. So if energy is distributed over a large space, it tends to have great disorder. If it's really tight and close together, it has less disorder. That's a spatial relationship. So it's often the case that we can kind of figure out how much entropy the energy has based on just looking at spatial distributions. Okay, so I'm going to show you the first example here, which is the Boltzmann distribution. This is a statistical look at entropy. Okay, so bring this up. There we go. Okay, so in this particular problem, it says that we want to calculate the absolute entropy using the Boltzmann hypothesis. So Boltzmann, we often think in terms of statistics, again, these distributions, right? An oxygen, which is O2 molecule, is adsorbed onto a small patch of a surface of a catalyst. It's known that the molecule is adsorbed to one of 576 possible states for absorption. See the sketch at right. Calculate the entropy of the system and round your answer to 3 significant digits, and be sure that it has the correct unit symbol. Okay, so if you look at the diagram over here, what we see is an oxygen molecule, O2, adsorbed. You probably know the word absorb, right? So like a sponge absorbs liquids, right? Absorption is when something goes inside, so the water goes into the sponge. Adsorption is related. There's a stickiness, just like with absorption, but it's the surface that we're talking about. So when an oxygen molecule adsorbs with a D to the surface of something, we call it adsorption. So absorptions go inside, adsorption is you go on the surface, right? So this oxygen molecule is adsorbed to the surface. And what they're saying in this problem is that it's, there's only one oxygen molecule, so it's in this state here, it's adsorbed right there. There are 576 different positions it could be, is what they're saying. And they want you to calculate the entropy. Now, the Boltzmann hypothesis says that there's a very simple mathematical relationship between the number of possible states and the amount of entropy, which they call absolute entropy. It's a statistical calculation. It's not a particularly complicated one, but it's one that we can use to do this calculation, okay? So essentially what you do is you say, look, there's 576 possibilities. So it's almost like I were to say, I'm rolling dice and I have one die, one cube, and I roll it. How many possible states are there? There's essentially 6 if we ignore the possibility that it lands on a corner or something like that, right? There's 6 possible states. So that's a statistical thing. The chances of it landing in one of those positions is 1 in 6, right? Now we're saying there's 576 different possible states. What's the amount of absolute entropy? It's a very simple calculation. So the calculation is, here, sorry. The absolute entropy, the amount of entropy is just K, I'll talk about that in a moment, times the natural log of the possible number of states. So here, this is what's called the entropy. They call it absolute entropy, meaning that you can actually calculate it. You're not comparing it to anything. This is called the Boltzmann constant. And it's not the rate constant, it's the Boltzmann constant, and its value is related to the gas constant R. It's essentially the gas constant R divided by Avogadro's number. It's 1.38065 times 10 to the negative 23. Notice the units are joules per Kelvin. So these are energy units, right? These are joules. And then this is Kelvin, which is a temperature, right? These are temperature units. So joules per Kelvin, okay? So all we have to do is take this Boltzmann constant, multiply it by the natural log of the number of possible states. Okay, it's a very simple calculation, right? So for this particular problem, we would take K, 1.38065 times 10 to the minus 23 joules per Kelvin. So there's your K, times the natural log of the number of states was 576. So there were 576 possible states. Okay. Now notice what happens to the units. The number of possible states doesn't have any units, so that's unitless. The units here are joules per Kelvin, right? Joules divided by Kelvin. So that means the entropy is going to be in joules divided by Kelvin. And those are the units of entropy. Typically are joules per Kelvin or kilojoules per Kelvin. something like that. Okay, so what I'm going to do is I'm going to go ahead and bring up the calculator so you can see it here. Okay, so here's your little calculator. This is from Microsoft Office or from Microsoft Windows. So we want to put in the K value. So 1.38065 times 10. So that's this EXP button to the 20 minus 23. So minus 23. Okay, that looks good. And then we're going to multiply that by ln of 576, right? So 576 natural log. And then hit equals just to get our answer. So it's 8.77556 times 10 to the minus 23. They wanted it to 3 significant digits. So 8.78, right? You would round the second 7 there to an 8 because the number after it is a 5 or greater. So 8.78 times 10 to the negative 23. And again, the units are joules per Kelvin. Those are the energy divided by temperature units. Okay, so in a sense, this is just a measure of how widely distributed the energy is. Okay, I'm going to go ahead and just show you one thing that is very common. So we got S 8.7. Sorry, let me bring this up. 8.78 times 10 to the minus 23 joules per Kelvin. It's very common to do it per mole. So in this particular problem, we're not doing it per mole. But if we were calculating entropy in joules per K mole, so per mole, okay, we would just multiply it by Avogadro's number. 1 mole of any substance is 6.022 times 10 to the 23rd number of particles, right? So we would just take our 8.78 times 10 to the minus 23 joules per Kelvin, multiply that by 6.022 times 10 to the 23rd per mole. Okay, and then you can see what's going to happen. Your units are going to be joules per K mole. Okay, the 10 to the negative 23rd and the 10 to the positive 23rd, that multiply those together, you get 1. So really all we need is that 8.78 times 6.022, and what you get is, 52.8 joules per K mole. So what you'll see, the reason I show that is not desired in the particular problem, but the reason I show you that is because what we're going to see is that it's pretty common that the amount of entropy of a substance in the units of joules per Kelvin mole is in the 10s to 100s. So like 50 or 75 or maybe 150, 200, but in the 10s to 100s range. Okay, that's if you have a mole of that substance. All right, so there's your introduction to entropy. Take